Okay, Assalamu alaikum. Good afternoon. Welcome to the second day of 2 days international webinar on recent trends in applied mathematics and physics. So I hope you had a great time yesterday, and today's session will also be very informative and useful for all of you. So I'm very pleased to introduce our first speaker, Dr. Galen Yoshev from Sofia University, Sea Climate ORIC, Bulgaria. So today he will talk about image creation of a thin accretion disk around black holes and naked singularities. So Dr. Galen.
Thank you, Sherish. I want to thank you first to all of you for the invitation to all the organizers of the webinar. I want to thank,
Thank you, sir.
yes, I want to thank and more especially to Dr. Sherish for the invitation. You know, maybe something for me, but I will introduce myself a little bit. So I'm researcher at the Sofia University. I'm a participant of this group, Sofia Relativity Group, where we considered a theoretical aspect of gravity and more especially theoretical questions which are very actual nowadays. So I chose exactly this title because it is very strongly related with the experiments in the astrophysics, more closely related with the relativistic physics of the compact objects like black holes, naked singularities, and wormholes. So you probably know that nowadays there is a few experiments which very successfully are trying to measure, for example, the physical parameters of the compact object as the mass, the moments of rotation of the object, and probably the charge if it exists, and so on. So let's mention some ideas which are very important and comes from the theoretical aspects of the problems. So first of all, if we imagine that we have a mass somewhere in nature, in the universe, we can imagine that this mass can deflect the light because of the effective mass of the light, which is related with the frequency of the electromagnetic waves. So if we assume that we have this kind of attraction between the mass of the object and the light, we can observe images of the light rays. And because of the shape and the intensity of the images, we can extract information for the physical parameters of the object, like mass, angular momentum, and so on. So in this way, we can differentiate between the different gravitational theories which take into account these physical parameters and suggest different geometrical and theoretical models which give us opportunity to understand the gravity nearby to these compact objects. So the other aspect of the theoretical consideration is the fact that this deformation of the images can be very special only for an isolated compact object like the black holes. And because of this, if we try to check more specially the deformation of the images, for example, we can check not only the mass and the spin, but and the multiple moments of the bodies. So this is very important because these multiple moments of the compact objects can give to us information not only for the rotation or the spherical symmetry of the bodies, but eventually for the deformation of the bodies because of the interaction with some other massive bodies which are nearby distributed with respect to this which we are considering. So if we go in this direction, we can take into account these external gravitational fields. Yeah, if it can be defined because of the existence of the matter nearby to the gravitational center, and defining this external gravitational field, we can obtain, for example, not one single shadow or images on the complex object, but we can define and find the multiple shadows, which is something very very famous today because of the colliding systems of two black holes, or a system of black holes and neutron star, and so on. Because of this theoretical aspect of studying is very interesting, and really it has to be taken into account. So the other aspect which we can consider is that the compact objects which we can study are not the classical compact objects which the general theory predict because of the Schwarzschild solution, which is the vacuum solution of the gravity equations. But we know that if this classical static and spherical symmetric solution predict existence of compact massive objects which a gravitational radius, which we can call the black hole horizon, we can assume that because of the Penrose conjecture, probably there exist naked singularities, which we know that they are compact objects, which possesses a physical singularity, which is hidden or have to be hidden inside this black hole horizon. And this is an interesting idea which can be checked and to see if these singularities exist, how they can be decoded from the images which they constructed because of the lensing. And every one of these ideas can be checked, and the final idea for the study and the observational defining of the images, we can concentrate our attention on the experiment Event Horizon Telescope, which started because of the collaboration of the maybe all the scientists which work in this field in all the world. And you probably know that before a few years ago, maybe 4 or 5 years, this initiative has started, and we know today 2 images which are constructed because of the gravitational lensing of the light of the probably existing black holes in the galaxies M87 and into the center of our galaxy. So these are 2 very, very interesting experiments, which give to us very encouraging information that it worth to pay our attention to this kind of problems. So because of this, inspired of these ideas, we try to study, or we can try to study some solution to the static and spherical symmetric equations of gravity. If we assume that there exists a scalar field, but a little more simple situation when the scalar field is massless, and if we take into account this information, we obtain these gravitational equations, which give to us the next solution. So we obtain a standard spherical symmetric metric for one element with these metric parameters here, but this coefficient in this situation describe not only the presence of the spherical symmetry, but in the most simplest situation, it represents the vacuum solution of the Einstein equations. and more especially the Schwarzschild solution. Because of this idea, we can use this metric to make a comparison of the gravitational lensing effects of the black hole, which is represented from the Schwarzschild solution, and a naked singularity, which in general this metric this metric shaped geometric. So if we take into account this metric parameter gamma, we see that the metric parameter depends on the mass of the complex object and on the scalar charge related with this scalar field. And if we change the values of the metric parameter gamma very successfully, we can move from the situation of the Schwarzschild solution to the naked singularity solution and to understand what are the observational differences between the black holes and the naked singularities in this more simple static and spherical symmetric case. So then, if we can proceed further with the gravitational lensing effects, we can write the metric and the line element in this general way. After that, taking into account in this static and spherical symmetric solution possesses separation of variables because of the Jacobi of the Hamilton-Jacobi equation. We can write the equation of motions in this very simple way and to study what is happening with the time. Sorry, what is happening with the time coordinate, with the azimuthal angle, and with the radial coordinate, and how they are changing with respect to the proper time of the particle. So, if we defined with this radial equation the effective potential, then we can proceed further and to study the stability of eventually existing orbits around the complex object, but this object to be more especially the orbits of the massive particles. So if we try to study these solutions of these equations and to understand is there exist, for example, a disk of particles which is constructed from these circular orbits, we can assume that taking into account this system of equation, which is not seen in a very good way now. So I will move this to show the system of the equation. So if we take into account this effective potential here, which is defined in the radial equation, and we want to obtain a circular orbit, so the condition for the circular orbit, which should be r equal to constant, gives us opportunity to see that the effective potential has to be zero and the first derivative of the potential has to be zero, because of this that we want to obtain a closed circular orbit. So in order this orbit to be stable, if we know these integrals of motion which are related to the motion of the particles, we can define by this way the energy of the particle. We can define the moments of the angular moments of the particle and the circular frequency, which you know that it is called Keplerian velocity of motion. So in the start from the spherical symmetric way, if we take this integral of motion, we can check are this circular orbits exist or not. So if we continue further, if we want to check are these orbits are stable or they are not stable, or in other words, if we want to see if at one moment of time we have a creation of a circular orbit and to understand after that is this orbit stable or it is not, and if it is stable to exist on a creation disk, so we can take into account one additional condition which gives us opportunity exactly the situation when we are starting to lose the stability, when exactly the second derivative became zero. So because of this, if we take into account these three equations, and if we solve this equation as a system, we obtain this equation, which in general is not so simple, but we really can understand for a given metric which are the radial coordinates for this circular orbit. And if we start to study this process, we obtain this effective potential, which gives to us the opportunity to see all the possible situations which are related with different integrals of motion, the energy and the angular momentum for a given Kepler and velocity of motion. And here we can see with the different colors a lot of different situations for different metric parameter and different integrals of motion. So we can see that there exist, for example, three different areas according to the distribution of the radial coordinate there. So we have two specific points are plus and are minus, which are related to the minimum of the effective motion. And this point gives us opportunity to check when we are starting to losing the stability of the orbits. So because of this, all of these points which are covered with red cover here represent the situation we have for stability, but in all the other situations with the black points, we didn't have stability. But after that, the interesting thing is that below this area, which is forbidden for the circular orbits, we have again other area which is more good seeing here in the right picture, where we can see again that we have appearance of these red dots. So in this situation, we can extract information for this that there exists again other table accretion disk which is within the outer accretion disk. So in other words, we have we have an accretion disk with a discrete structure. So we have outer and we can observe eternal accretion disks which are closely related one to other. So in order to show more simple this situation, here we choose three different values of the metric parameter gamma, which involve in itself the charge, the scalar charge of the scalar field. And we see that in these situations, for example, this first situation, we have a single accretion disk. So here with the red color, we have the innermost stable circular orbit related with the outer accretion disk. This orange curve, dashed curve here, represents the existence of an open sphere, which about which I will speak a little bit further. But here within the center, we can see other area which is related with the naked singularity itself. So here we can observe the singularity of the richest color, which means that we didn't have opportunity to consider what happened inside this area. So if we change this metric parameter, or with other words, if we change the mass and the value of the scalar charge, we start to observe two accretion disk. So we have outer and inner accretion disk and small gap, the tiny gap which is within the disk. And because of this, this probably will give interesting observation of features after that, and we can understand what is the structure of the disk, and probably to understand more carefully what is the geometry of the space-time nearby to the compact objects. And we have one-third situation in which for a smaller value of the metric parameter, this tiny gap starts to disappear, and we have only one, which starts from the naked singularity, which is represented here with a solid black color, and can continue to infinity. So, because of this, we have a lot of mathematical situations which we have to take into account. So you can see that the task is very wide for examinations. But if we want to study the gravitational lensing effect, we have to consider other part of the task. So the first part which I was mentioned until now was related with the stability of the disk. But we have in the second part of the distribution of the white rays, which start to appear because of the friction of the particles within the disk. So because different circular orbits are specified with a different Keplerian velocity, this means that two nearby orbits which are very closely related one to other will move with a different velocity, which means that they are physically, if we physically considering the question, we can see that we will obtain a friction between the particles, and because of the friction, we have emission of white rays with a different frequency, and if we are studying the distribution of the white rays in this geometry, we can understand what is happening with the lensing. So in order to study this direction of the problem, again we are considering the radial equation of motion, because it is the most interesting from all the other equations. And this equation can give us opportunity to define an effective potential, which is related to the constants of motion with the moment of rotation of the particle of the photons. And if we use again the system of equation which is applied over this effective potential, we can understand when we have stable photon orbit or unstable photon orbit. So why this problem is interesting? Because if you want to observe and to extract visible information from the astrophysical processes which are realized nearby to the compact object, we want to send a photon to the Earth, which is emitted from some white source into the universe. And this photon have to go to the compact objects to take a little bit time around the compact objects to extract the information from the objects, and after that we have to tell to these photons to come to the Earth, and if we see the photon, we can study all the features which are related exactly with this specific photon, and to understand what is happening with the compact object. So because of this, we are not interested from the photon orbits which are stable, because if we send a photon to there, this photon will remain a lot of the time nearby to the compact objects, and we can believe that it can turn back to us. Because of this, we orient our attention to the so-called unstable state of photon because they are more not so hard for studying. And because of this, that they are unstable, we can believe that when exists some small perturbation of the energy or of the angular momentum, this photon can escape from the complex objects and eventually to turn to the Earth and to see what is happening with the geometry of the space and the time. So this physical interpretation gives us the idea to concentrate our attention to the effective potential and to study exactly these points where we can observe local maximum of the potential, which is related to the instability of the orbits. So because of this, if we study this, here, for example, with the black curves, we can see the information for the Schwarzschild solution, but the other curves are more interesting. So they give to us the information that we have a situation with instability, and we have some other situations because of this purple curve here, which give to us the idea that for everyone, energy and the moment, we have something very interesting. We have the opportunity, the photon, to go to the singularity and to turn back. So it can see the singularity as a mirror, or the singularity will reflect the photon back, and it will be oriented somewhere into the universe. So this is very character situation for the naked singularities, because they have a repulsive potential about the photons, which is very interesting and difficult situations related to the effective potential of the black holes, which we can see from this black curve that we doesn't have opportunity to of a turning point. So the most big part of the photons will be trapped of the black hole horizon in this situation. Okay, so then if we continue further.
Excuse me,
yes.
Dr. Gallic. Sorry for the interruption, but we will resume the webinar after a while. Please rejoin the meeting on the same link. Thank you.
Okay, thank you. So the photon sphere, we can relate the radius of the photon sphere with the integrals of motion of the photon, which are labeled here with eta and zeta. And if we have this information, this means that we can study the trajectory of the photon. So we know everything. We know the whole destiny of the photon. So what is happening from the time of the excitation of the photon from the light source, the time during the time of the traveling of the photon, after that, and to the receiving of the photon from the observer. Because of this, we can make a mapping. So we can relate the space of the integrals of motion with the so-called celestial coordinates, alpha and beta, which can be defined as a two-dimensional spherical or flat coordinate system over the observational sky. So if we have this opportunity, we can calculate the celestial coordinates from the equation of motions, but more especially from the asymptotic behavior of the equation of motions at infinity, where we are assuming that the observer is situating during all the time. So in this case, we can make this mapping between eta and zeta and alpha and beta, and we can understand how our images, because of the lensing, will be observed over the sky. Then, in order to make this we have to take into account and all the solutions of these equations. So in this diagram, for example, are represented the solutions of the ISCO equation and the solution of the open sphere equation and the solution of the singularity, of the curvature singularity of the solution. So, for example, with the red color and the blue color, we can observe the positions of the ISCO orbits for the external and of the internal part of the accretion disk. So we can see, for example, that for some specific value of the parameter gamma, for example, 0.8, if we take it, we can observe only one solution. This means that we have only one ISCO orbit, and all the space outside this radial coordinate is connected with stable time-like orbit. So we have an accretion disk here. But if we are choosing metric parameter gamma, which is here below 0.5, we can see two solutions, the red and the blue one, which means that we have accretion disk with discrete structure. So it is specified with a very small gap between the internal edge and the external part. The orange green, the orange curve represents the photon sphere. So this is very important when we study the astrophysical processes to take into account where the photon sphere is positioned, related with the orbits of the disk. So we, for example, cannot observe a time-like orbits within the photon sphere. So this is not possible because they cannot move with a speed bigger than the speed of the light in vacuum, which means that really the photon sphere should be here in this place, and it is really very closely positioned with respect to the compact object. But here the black curve represents the curvature singularity. So this means that all the possible solutions of the equation have to be taken into account above the curve, because we can define the space-time and we can define the manifold of the space-time there in this space. Then in order to study the gravitational lensing, here I am presenting one classical situation when we have a stable circular orbits mentioned with the purple color. We have some arbitrary white point which emit a light represented with the red color, but we see that some white points labeled with blue color are oriented to the compact object, which means that really we have two parts into the space-time, which are related with the objects, with the orbits, with the photon orbits, which can hit and can enter to the complex object, and other orbits which are scattered with the complex object and can hit over the photon sphere, which is shown with this circle here. So really, this means that if we choose some very special value of the impact parameter of the light rays, we can hit and to move over the photon sphere which exists when the space-time is static and spherically symmetric. So the other interesting thing here is that because of the existence of this photon sphere, the photons which are moving very closely to the photon sphere can make a lot of windings around the photon sphere, and if these photons make this, they can extract more strongly and more powerful information from the object. And if the photons turn back to us, we can understand what is the geometry of the space and time. In order to make this, we can study the deflection angle, which because of the metric coefficients, take this one. And if we considering the position of the observer, we can understand that the angle of the light, the detection angle of the light is related by this way with the inclination of the observer and some parameter eta, which can take this opportunity to move the light rays and to choose this light ray, which is more interesting for us. But the other part, which is more fundamentally interesting for the light, for the deflection of light, is that this light ray, this deflection angle can become infinitely bigger. And this is exactly the situation when we have a lot of windings around the photon sphere. Because of this, the behavior of the function of the deflection angle can be approximated with this k multiplied with pi, where this k is integer number, and the second term here represents the position of the observer. In other words, this equation can be called a lensing equation or the gravitational lens equation, and it can give all the information related with the images. So here we take into account the different behavior of the detection angle as a function of the impact parameter b, and we see that because of the different values of the angle, where this is the azimuthal coordinate, we can see that we have area with zero windings. We have area with winding with two, and so on and so on. We can continue to infinity by this way. And for every one of these different areas, we can observe one single image. So, for example, this which is shown with the orange color here, this is the so-called direct image. After that, the blue one is the indirect image, the first indirect image, and the blue one is the second direct image, which is related with the photons which are turning 2 times around the photon sphere. So this image is very closely positioned to the photon sphere, or it is related with the photon sphere itself. So this situation, which I show you here on this slide, is related with the existence of the photon sphere. But in this situation, we have not a photon sphere. So we have this very interesting case when we doesn't observe a photon sphere, because the scalar field is not so stronger to give the opportunity to the compact object to create the photon sphere. And we can observe some other characteristic features of the imaging, which probably can give us the opportunity to differentiate the naked singularities of the black holes. So then applying this idea for different orbits, so orbits which are more further from the gravitational center, we can see that the images has a different structure. For example, if we take all these situations, for example, this situation here and this situation here, and study the whole different possible orbits of the disk, we obtain these images. So we see that they are very strongly related with the results of, for example, one person which is called Jean-Pierre Luminet from France. So he studied for the first time such kind of images for the Schwarzschild black hole solution, and it has exactly this structure. So we again have the primary image which is with the orange, we have the indirect image. We have this black indirect image, which is related to the focus sphere. But if we are going to study not only the black holes but the naked singularities, because of this specific structure of the diffraction angle, we obtain internal images which are not which are not specified for the black holes. So this is one of the major differences to obtain images which has internal structure. From other point of view, we have the second disk. So this internal disk. This internal disk is represented here, and different lines, for example, represent the so-called ISO radio lines. So which give us opportunity to understand the structure of the image. So which exactly orbits from the disk are related to the specific points or areas or lines over the image. So because of this, we can understand the formology of the disk. And if we taking into account the different inclinations of the observer with respect to the axis of the solution, we can see the different images related with this is of the black hole solution, and this is of the naked singularity solution. So we can see that again we obtain more difficult structure of the images. And this is again the internal disk. Okay, so if we continue further and study the whole ray tracing, so if we apply a ray tracing and follow the path of the photons, and take into account one of the most simplest models of the thin accretion disk, which is developed of Novikov and Thorne. We can study what is happening with the distribution of the density of the energy over the disk. And if we take into account this distribution of the energy and how it is related or how it is transformed for a distant observer, and taking into account the Keplerian velocity of the motion of the particles into the disk and the redshift effects due to the curvature of the spacetime nearby to the contact object, we can see this disk. So we see that because of the rotation of the particles which are moving toward us, we obtain this higher temperature area here on the left-hand side, but the other area which is related with the redshift, not of the blue shift, we can see a smaller temperature there. And if this is for the black hole, this is for the naked singularity. So we can see the differences and the internal structure. But this is now the whole story. If we continue further and applying different inclinations, so this is the other inclination for the black hole, and this is for the naked singularity, we can obtain by this way the whole visible structure of the disk if we study by the same way and the internal accretion disk, which is closely related to the naked singularity. And we can see here inside the object that we have additional images which are related with the internal disk, and in general they possesses a flux intensity which is very bigger with respect to the flux of the outer image, which is really which gives us really the opportunity to observe very easy the naked singularity with respect to the situation of the black hole solution which where we obtain this standard calculation disk. So, in other words, we obtain not only the different shape of the hinges, but we obtain a different distribution of the energy, which gives us opportunity to use instruments with maybe more or less ability to measure the intensity of the light, or just more easily to detect images which are related with naked singularity. So with other, so there exists another situation that so other problem which nowadays is trying to be solved, that because of the size of these images, and more especially that the size is very, very small. So the size of the whole disk is probably 10 micro arc seconds, and the shadow which is inside is probably 50 microseconds. This means that it is very difficult to be observed, and we are needed of a very long baseline interferometry with a very long size, which can be difficult to measure this internal structure, or just to see this internal structure, which is very, very hard. Okay, and these results, these theoretical results are published in these two papers. So if you're interested, you can search for the information there. So in general, this was my talk. So I want to thank you once again for the invitation, and more especially to Dr. Sherish for the communication and for this very kind invitation. So thank you very much.
Thank you so much, Dr. Galen. So time for questions. Questions from the audience. I think Ms. Sadia Karim has a question. So Dr. Taiba, can you please unmute her? Ms. Sadia, you can unmute yourself. Yes.
Assalamu alaikum. I have a question.
Hello.
Does time stops at the singularity?
Sorry, related with the time structure of the singularity. Sorry, can you repeat it?
Sadia, can please repeat your question?
I said that does time stops at the singularity?
Do you mean the singularity? But what exactly with the singularity? The motion of the particle, the device, or the structure of the singularity, the structure of the solution? If you can precise the question, I can understand it in a more good way. Please.
Okay, thank you. So I just had one question that one student typed in the chat box. Let me check. Miss Zani Ilyas typed some question in the previous meeting. Yes. So she was asking. Okay. Yes. Do we have time?
Yes.
Yes.
Okay. She actually typed, what is the main difference between images of black holes and naked singularities?
Yeah. So exactly in this slide, which we can see now, we have the major differences between them. So if here to the right part of this slide, we have this single accretion disk. So this is the most standard situation. We have the direct and the indirect images, but here into the situation of the naked singularity. Instead of these situations which is character for black holes, we can see inside this internal structure of the disk. So I will move in this slide, which more precisely can show this difference. So if we consider these images, which represent the images of one single orbit of the disk, so we can see, for example, these three different images. But this is the situation when the black hole has a photosphere. If we move to the situation in the next singularity, we can see the case when we observe one additional image. This is the so-called second direct image. And this is maybe one of the most distinct feature of the images, which is character for the naked singularity with respect to the situation of the black holes. So I can answer by this by this way, because this is the most simple answer. But if you want to study more deeply the question, we have to consider and to study this function here, and you will understand that for the different parameters of the light rays, which are related here with this impact parameter, we have different solutions. So we have different areas, for example, in this part here and in this part here. And because of this, we can, when we have a naked singularity, we obtain the opportunity to observe not only one, but a lot of different number of images.
Okay, thank you. Okay, Zeni. Thank you so much, Dr. Gellin, for such a nice presentation. And for the audience, Dr. Gellin is a theoretical physicist, and he has excellent research work in black holes, gravitational lensing, and shadows. So thank you so much. Thank you, Dr. Gellin.
Thank you, Dr. Gellin.
Okay, so let's move on to the next speaker, Dr. Samit Mamish, Assistant Professor, Department of Computer Engineering, Istanbul Rumeli University, Turkey. And his main area of research is fuzzy sets, soft matrices, machine learning, and CN making. So, Dr. Samit Mamish.
Hello, dear professor. And now I can prepare my screen. Just a sec, please.
Okay.
Dear Dr. Gellin, by the way, thank you for your wonderful presentation.
Thank you very much.
If you can close your screen, I can share my screen.
Yeah, I
apologize.
I can try to close my screen, but can you help me? Yes.
You can use stop share.
Yeah. Thank you, Dr. Gellin.
You're welcome.
Excuse me, Dr. Samit. I think it will be good that we will resume our meeting after a while. So please rejoin the meeting on the same link. Thank you.
Thank you. I think you can see my screen now, right? Thank you. I would like to present the study titled Machine Learning via Soft-Set-Based Concept today. My presentation is in 6 parts, as you can see in the screen. Soft-sets, being a standard and practical mathematical tool, are often used for modeling uncertainties, and a great variety of studies have been conducted on this concept. Fuzzy soft sets, fuzzy parameterized soft sets, fuzzy parameterized fuzzy soft sets are among general forms of soft sets. Also, studies on the matrix representation of these sets have been increasingly continued, such as soft matrices, fuzzy soft matrices, fuzzy parameterized fuzzy soft matrices. Even if parameters and object have uncertainties, the FBFS matrices can successfully model such problem. In my PhD studies, generally I studied the FBFS matrices and their application in many areas, machine learning or image processing as well. And I can show you the relationship between them. You can see in the screen, and the subset or matrices, fuzzy subset, fuzzy parameterized subset, and the top of the fuzzy parameterized fuzzy subset, and the FBFS matrices in short. And FBFS matrices is capable of the modeling many uncertainties, and so that it's very useful for these properties. Of course, there are many upper structures, but the uncertainties faced in our real life, and it can model the many uncertainties in the real life. We can model the uncertainties using the FBFS matrices. The rest of the study is organized as follows. In section 2, the following definitions are presented: FBFS sets, FBFS matrices, pseudo metrics of FBFS matrices, pseudo similarities of FBFS matrices. In section 3, machine learning and well-known machine learning approaches are provided. In section 4, the following recent machine learning approaches via subset-based concepts are provided. Fuzzy subset classifier, fuzzy subset classification using distance, Hamming distance, and fuzzy parameterized fuzzy Euclidean classifier. Comparison matrix-based fuzzy parameterized fuzzy soft classifier. Aggregation operator-based fuzzy parameterized fuzzy soft classifier. Fuzzy parameterized fuzzy soft k-nearest neighbor. They are the subset-based machine learning algorithm, actually. In the final section, some suggestions are made and some conclusive remarks were provided for further research. In this section, firstly, the concept of FBFS matrices have been presented. Throughout this paper, let E be a parameter set, Fe be the set of all fuzzy sets over E, and mean Fe. Here, a fuzzy set is denoted by, like that, instead of this. Here, we can see the definition of the fuzzy parameterized fuzzy subset. In the present paper, the set of all FBFS sets over U is denoted by FBFS EU. In FBFS EU, since the graph alpha and alpha generated each other uniquely, the notations are interchangeable. Therefore, as long as it does not cause any confusion, we denote an FBFS set graph alpha by alpha. Here, an example of the FBFS set. I want to explain on this. Here, the parameter set E and the alternative set U, and we can parameterize it, the alternative sets. For example, these sets can be house alternatives, and these are the parameters related to houses. We can, for example, we can express the house selection problem using the FBFS set. In fact, here there are many membership. These memberships are fuzzy value, and we can express the problem using the FPFS set like that. Here, the definition of FPFS matrix, and it's related to FPFS set. And we can say that the matrix representation of FPFS set, you know, we need this representation because we can't write a set on the computer, because we can something write on the computer using matrix or some array. So we need them to computer math. Throughout this paper, the set of all FPFS matrices parameterized via E over U is denoted by FPFS EU. This is the example of the previous example. And you know, the previous example is related to an FPFS set. Here we can see the FPFS matrix of the previous example, and the rows related to alternatives, and the columns are related to parameters. Attention please, because the first row is related to the importance degree of the parameters. For example, the membership of the x1 0.5 or 0.5 you can see here. And for example, the membership of the U1, but the X3 and U1. And you can see that the third column and the second row and third column here. And we can construct the FPFS matrix like that for any problem. Secondly, we present the pseudo matrix and pseudo similarity of FPFS matrices. I think the generalized metric functions in the general topic in the math, but here we can use this concept on any different spaces. For example, FPFS matrices space, another space, and you know the many set theory in the math. Fuzzy set or soft set or intuitionistic fuzzy set, and many hybrid versions of them are there in the math. And the generalized similarity is defined in our study. And for example, the definition let S mapping, and for all x, y, z in X, the S1, S2, S3, and S4 denote the following properties. Now we can define the generalized similarities. S is called similarity if S satisfied S2, S3, and S4. We know the similarity definition because it's the general concept, but the others generalized similarity, you know. And S is called quasi-similarity if and only if S satisfies S2 and S4. Let's look the S2 and S4. S is called semi-similarity if and only if S satisfies S2 and S3. Here, S2 and S3. And the last one, S is called similarity if and only if S satisfied S1, S3, and S4. You can see the properties. Now, I mentioned some pseudo-similarities of FPFS matrices. For example, the Minkowski pseudo-metric of AIG and BAG in FPFS matrices spaces. You know, we can use the many metric function in math, but these are different from them because these pseudometric or these metric function, this pseudometric function, based on the weighted metrics. Please attention the formula, because the A0J is the important degree of the parameter. We can weight the metrics using the importance degrees of the parameters, and these affect the all process, decision making or classification in machine learning or anything. So this is important concept in the pseudometric. And of course, this is the generalized, because if P is equal to 1, and it's called the Hamming pseudometric, or the P value is equals to 2, and it's called the Euclidean pseudometric, and denoted by DH and DE respectively. The other one, Hausdorff pseudometric, generalized Hausdorff pseudometric. As you can see here, the p-value is equal to 1, and it's called the Hausdorff pseudometric and denoted by DHS. Now, I can mention the Minkowski pseudo-similarity. And here, this similarity is based on the pseudometrics, you know. And we can use the pseudometric, we can define the pseudo-similarity easily. And the others are defined the similar way. Now, I can say something about the machine learning in general. The machine learning or artificial intelligence is the very popular topic in the world. I think everybody knows this concept. But I mentioned some of the general properties or general thing. The amount of data being gathered by technological advancement is constantly growing, we know. The machine learning is one of the most popular concepts used to acquire meaningful data, imitate the human decision making, and deal with many uncertainties. Several industries employ this technology, including the defense sector, meteorology, psychology, finance, medicine, astronomy, and space sciences. Among mathematical tools, fuzzy set and soft set stand out as able to describe real-world problems involving uncertainty. So the main idea to study these two concepts, we always modeling uncertainty using the soft set or the hybrid versions of soft set. And the other area, for example, machine learning, try to modeling uncertainty, and we say to each other, we can use them, we can combine them to enhance the modeling ability, you know. It is essential to develop new approaches or improve well-known machine learning techniques using mathematical tools to analyze data in these sectors more efficiently. Therefore, a viable strategy to improve the performances of machine learning algorithms is to combine them with fuzzy sets, soft sets, or their hybrid counterparts. Numerous techniques have been developed over the past 7 decades, including k-nearest neighbor, and this is the very popular machine learning method, support vector machines, and as well, fuzzy KNN, decision trees, and random forest. Additionally, their many improved versions have been suggested for real-world problems, and it continues. Here we can see the subfields, the machine learning subfields of machine learnings, and the machine learning splits into 4 subfields, and they are supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. In our studies, we focus on the supervised learning. And in the soft-set literature, the supervised learning are focused as well. The crucial problem in soft-set literature is that the applications are designed for fictitious problems. These are a really important problem because the soft-set or the soft-set-based concepts can be modeling uncertainty very well. But many studies based on the fictitious problems. I think we know the many article title, for example, medical diagnosis or decision analysis or anything, but the many of them based on the fictitious problems. This is a really bad problem. I think we can enhance the real application in our literature. I think. Especially the number of studies related to machine learning is deficient. The machine learning approach is based on soft sets, fuzzy sets, and fuzzy soft sets are as follows: the soft set classifier, fuzzy soft set classifier, fuzzy sire, fuzzy soft set classification using chemical distance. These are very deficient. For example, I show them and the algorithm steps in shortly. The soft set classifiers algorithm steps and the fuzzy soft set classifiers algorithms step. Fuzzy sire as well. Fuzzy soft set classification using chemical distance and the last one. And we examine these studies, and but they are very limited to apply any real data. So there are many databases in the internet. For example, UCI, Kiel, Kaggle, and we can propose a new approaches for the many data set in the real world. In 2021 and 2022, we proposed new machine learning approaches using FFS matrices. These are fuzzy parameterized fuzzy soft Euclidean classifier, comparison matrix-based fuzzy parameterized fuzzy soft classifier, aggregation operator-based fuzzy parameterized fuzzy soft classifier, and the last one is the fuzzy parameterized fuzzy soft key nearest neighbor. The mutual properties of these concepts. In the previous slides, I provide the pseudo similarity. And the pseudo similarity is capable of the modeling classification problem in machine learning and consider the parameter impact. We can use the parameter impact in the machine learning due to this pseudo similarity concept. And we obtain the parameter effect using the Pearson correlation coefficient or Kendall or Spearman correlation coefficient. And this process enhanced classification performance. We see these results. Anyone wonder the numerical results of these studies? You can see our article, or I can share the article with you with my pleasure. These working principle or algorithm steps in screen, the FFS EC and general working principle in machine learning, in classification or supervised learning. We split the data, split into the data two parts, and training part, testing part. And we use the training parts, and we aim to gain the experience in our algorithm, our model, then we test our model using the test data, because the train and test data has the class labels. We can test our algorithm using the test data. Then we can compare the existing methods and our method or methods. Comparison matrix-based fuzzy parameterized fuzzy subclassifier, the FBFS CMC, and the next one, FBFS EC. These are similar because in these two algorithm or classification algorithm, we use the multiple similarity function, pseudo similarities of FBFS matrices, and because there are many different abilities. There are many different abilities in these pseudo similarity, and we don't know which one is the successful pseudo similarity for which data set, so that we aim to use simultaneously these pseudo similarities, and we can do this procedure using the soft decision making method, and we construct matrices, FBFS matrices, using the pseudo similarities values, and then we calculated the parameter effects of the pseudo similarities, and the last procedure in the algorithm, we use the SMBRO1 soft decision making method, and we decide the optimum training sample, and we assign the label of the training sample to the test sample, and this procedure go on all test samples. Here the some differences, because the FBFS K nearest neighbor is different from the K nearest neighbor, because the basic, in shortly, the KNN algorithm based on the single metric function. And here we use the 5 pseudo metric to classify the test samples. And here we use 5 pseudo metric of FBFS matrices, and we obtain 5 K nearest neighbor, and we decide to evaluate all K nearest neighbors, and we assign the label to the test sample. As you can see in the algorithm steps. It looks some complicated, but anyone wonder the details, I can share the article, or I can share some extra documents. Contrary to most of the studies in the literature working on a fictitious problem, we applied the similarity measures of FBFS matrices to actual numerical data classification. In the simulation of the algorithms, we utilized the real data set provided in UCI machine learning repository, and I set the others, the Kiel or Kaggle, or many different database you can access in the internet. We then compare the performance of the algorithms by using the 4 performance criteria: accuracy, precision, recall, and F measures, and they are defined by, as you can see, and these are the popular performance metrics in the supervised learning. Here, the accuracy of a classifier is calculated by dividing the total correctly classified positives and negatives by the total number of samples. The precision of a classifier is calculated by dividing correctly classified positives by the total positive count. The recall of a classifier is calculated by dividing correctly classified positives by total true positive class, and the F measure of a classifier is harmonic mean of precision and recall values. FBFS matrices can model classification problems containing uncertainty about which parameters being more effective to classify data. Therefore, it is worthwhile to study developing different classification algorithms by using different similarity measures of FBFS matrices, because success can be increased by using different datasets and membership functions. Moreover, different classification algorithms also can be developed by using soft decision-making methods via FBFS matrices, such as in these references. Additionally, aforesaid studies also gives an inspiration about how to construct FBFS matrices for real-life problems such as data classification. And the construction of FBFS matrices according to the problem is very important, because it depends on the problems, type of problems. These are references we used in our studies. Thank you to listen to me. And by the way, I would like to thank the organizing committee and Dr. Taiba and Dr. Sharif. Thank you for inviting me to this webinar.
Thank you, Dr. Samit. Thank you very much. We are really grateful to you for your such a nice, informative talk and your innovative ideas. Thanks once again.
Yeah, thank you, sir.
Okay, Dr. Sarish, you will continue.
Okay, any questions from the audience? You can raise your hand, or you can type in the chat box.
If any question after presentation or any time, they can email to me for their questions. I will help with my pleasure.
Okay, thank you. So I guess no question this time. So thank you so much, Dr. Memish.
Thank you, Dr. Sharif. It's my
Okay.
This is my pleasure. Thank you.
Thank you. Someone was asking question.
Yes, ma'am. I'm Samia.
Okay, Samia, please go ahead.
Okay, sir. I'm sorry. मैंने आपका session late join किया थोड़ा, but
Samia, he cannot understand Urdu. Please speak English.
Okay, ma'am. Sir, I want to ask.
Yes, I'm listening to you.
What is the black hole? I can't understand.
Samia, I think you have joined late. So, okay. So thank you so much, Dr. Memish. Hope to see you again.
Thank you. She can email to me for question, by the way.
All right, sir. Thank you.
You're welcome. You're welcome.
Okay, I have an announcement. Unfortunately, Dr. Ghulam Mustafa is not able to join us today as he's having some health issues and he has been hospitalized this morning. So we are praying for his speedy recovery. So we have to move on to our next speaker, Dr. Zishan Yusuf, Associate Professor in Mathematics from University of Punjab. He is ranked among top 2% scientists worldwide, and his main area of research is gravitation and cosmology. He's mainly focused on gravitational theories, compact objects, dark energy, dark matter problems, and cosmology. So, Dr. Zishan Yusuf, over to you.
Thank you very much. I will. Hello, can you listen me? Hello.
Yes, sir.
Okay, thank you very much. Thank you very much for inviting me for this on this recent trends in applied mathematics and physics. I would like to say special thanks to Dr. Saif Iftikhar and also Dr. Rubab Mansoor and also Dr. Taiba for
Thank you.
inviting in such a nice and exciting event.
Thank
So
you.
my title of my presentation is Kozai homologous evolution and Bronsted theory. This is very important type of homologous evolutions. Such kind of evolutions is often related to the object when they suffer from several dynamical activities. And for example, if we want to assess the complexity of non-static systems, so one can consider the evolution pattern besides physical matter variables like this, that this is the simplest evolution mode in which the collapse of a sub or any object is having a special type of constraints. That is, u is directly proportional to r, where u is the velocity and r is the metric coefficient corresponding to the r and theta and phi coordinate system in the spherical systems. Okay, that is u is in other words we can say that the u, which is the fluid flow
Uh,
velocity, is directly
Dr. Zishan,
proportional to. Yes.
Dr. Zishan, I think the slides are not moving.
Yes,
Uh,
I'm here. I'm in the first slide.
all
I'm
right.
just
Thank
trying to
you.
explain the
Sorry.
Akuzai
Sorry for the
homologous evolution.
interruption.
Okay,
Okay. Thank
so the fluid U is directly proportional to the proper radius. For example, if we have a body and that body has some structure, I assume that that structure is spherical in shape, and that spherical shape has some radius. So R, okay. Next, I will assume that this geometric structure is coupled with a fluid distribution. And that fluid distribution has some force velocity. So if the force velocity is proportional to the radius r or proper radius r, then we can say that this is a quasi homologous evolution. Okay, if a system passes through several dynamical activities in such a way that the fluid force velocity is directly proportional to the proper radius r, then we call this to be a homologous evolution. From this one can get the quasi homologous evolution, which is the most less strict condition to count for the evolution pattern. Okay. Next, there is a Bronsted theory that I will use it. This is one of the modified theories of gravity, and this comes as a modification of general relativity, and we know that general relativity is the basic ingredients in the relativistic astrophysics. Okay, so we are talking about the quasi homologous evolution of a complex systems. And what are complex systems? Actually, I'm going to tell you each and everything from the basic definition. That is, the system is the term that originates from the Latin word systema. It is described through its unique structure in which all the ingredients are specifically organized. We have a system, all the ingredients are inside here, and they are organized in a specific way. The nature of the system may be altered by the influence of internal factors. For example, if I apply some force over that is external force. If there is a nuclear fission or nuclear fusion reactions, and that comes from the internal body, so that's what could be called as internal force. So the change will occur in that complex system due to external forces or due to internal forces. So the systems whose structure is complicated because of the irregular arrangement of their components. For example, if we have a system and it is complicated because it contains many phenomena that is acting over that, maybe it is outside or maybe it is inside. So we can call this to be as a complex system. So amalgams of all various kinds of factors accountable for producing complications in any structure define the complexity of the system. Okay, so this is really a very good activity to organize such a good events, recent trends in applied mathematics and physics. So I would really like to say special thanks to the organizers and also the whole college, Lahore College for Women University, for inviting me from the Department of Mathematics, University of the Punjab. So the content of my title is, so first of all, I will describe some introduction. In the introduction, I will describe you how I came to know about this phenomena or about this process, which I will explain here. Next, there will be the motivations. Who motivated me to do work in this direction? Who makes me to think like that? Who makes me to calculate the calculations, to form the equations and find the solutions? I will discuss afterwards. And then I will present some research work, the work which is considered to be a new one. And I found that this could be a very good addition in the field of relativistic astrophysics, applied mathematics, and mathematical cosmology. And the last, I will describe you my conclusions in the nutshell. I will describe few points, and I will try my best to present my results in just 3 or 4 lines, so that one can understand what was my conclusions after having after this heavy calculations and results and discussions, etc. So the self-gravitations, you know that self-gravitation is a very good phenomenon in which all the objects are connected with each other, and they are producing some gravity because of the internal phenomena. If the system is in equilibrium, then it will stay there, and because of some interchanges in it, we will have some self-gravitations, and then we will find some alternative theories. And for this, I would like to explain some very brief history on that. What is that? Because of the Big Bang, our universe was once an infinitely dense and extraordinary hot, small point resembling a mathematical infinity. Okay? And that since the mathematical infinities are irrational when it comes to the physical equations, so the comprehension of universe at that infinite scale is elaborate. Due to some unidentified reasons, the space starting inflating. Okay, because inflating means now the inflation occurs. It endured an exponential expansion. Inflating means it endures an exponential expansion phase, driving apart all the constituents of the universe. Now,
Excuse me,
all the
Dr.
constituents of the universe, they are.
Dr. Zishan,
Hello.
sorry for the trouble,
Yes.
but you have to rejoin on the same link because we are running out of the time. Sorry.
Oh,
Please rejoin.
okay. Thank you so much. Thank you so
Okay.
much. Okay. Thank you so much. Should I stop? Universe was endured in exponential expansion phase, driving apart all the universe cosmic constituents. It means all the constituents of a universe, they were moved away from each other. The distance between them increasing time to time, and owing to such an expansion of our space, the temperature dropped down, which resulted in the collision of protons and neutrons present in the space. At that time, there was in the space, there were protons and neutrons, and because of the collisions, the temperature dropped down, and this phenomena produces deuteriums. And deuterium, what is deuterium? It is, that it is an isotope of hydrogen gas, which in turn combined to become helium. So what we did, what was at that time, there were neutrons, protons, they collided with each other, and the temperature dropped down, and because of the deuterium presents, and then which combine again to give helium, and that was the elementary ingredients for star formation. Okay. Now, the observation from NASA demonstrated that minor fluctuations in the matter density generated a gravitational pull that produces enormous cosmic web-like configuration of stars in space. Okay. So at that time, you know that there will be many things that comes because of the special relativity in which the space and time are deeply connected. In fact, they are one and the same, a flexible fabric called space-time. And Einstein produces the special relativity, but after soon he realized, after re-examining his theory, that his theory is severely restricted, as it can only be applied for a special case. What was a special case? An object moving in one direction at a constant speed. So he decided to generalize his theory from special to general theory of relativity. Soon it found some, it suffered from some problems, because Albert Einstein propounded in GR, which emerged to be the very good functional theories for which beneficied many peoples in the relativistic astrophysics. The basics of GR lay down upon the space-time structure, local causality, and the equivalence principle, and also the local coordinate fields. It shed lights. What the shed lights? It shed lights on the fact that space-time is differentiable manifold having 4 dimensions and Lorentz signature that you can use to be plus minus 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 or minus plus plus. What he did in this theory, he actually coupled the matter sources and the metric via his non-linear equations of motion, famously known as Einstein field equations. So what are Einstein field equations? These are just non-linear partial differential equations. So whenever a person talk about Einstein field equations, it means he is talking about a non-linear partial differential equations. But normally there will be a one partial differential equation, but Einstein presented set of equations in the form of indices whose dimensions or whose variation gives you number of terms. For example, if you are playing with 4 dimension, alpha beta has four coordinates 0, 1, 2, 3, 4, it means that field equations are having 16 components in which there will be independent and there will be dependent. So it means we have a number of equations. So what are these? Einstein field. Einstein doesn't mean this is related to physics. Yes, this is related to physics because I have many applications, but they are related to, we can call this to be, we should tell them to be Einstein, non-linear partial differential equations. Once we have a differential equations, one can solve them, one can find the solutions, one can check the physical applicability of these solutions, one can see the applications of the solutions. That's the main problem that we want to discuss in our currently in relativistic astrophysics. Okay, so from this we will get the alternative theories of gravity, and then there will be Brownian theory of gravity, because I know that there's a huge discussions over the Einstein, over the alternative theories of gravity, because the alternative theories of gravity recently, or we can say that yesterday, I listened 2 to 3 lectures and the same event, and that was the lecture given by Professor Ulmo, and then Dean Faculty of Science by Dr. Rizwana Kosar and Dr. Mohammad Zaimul Bhatti. They described the what are the applications and how we get alternative theories. So that's why I want to skip that portion. So next I will describe the Brownian theory. It's a scalar tensor field theory. Consider, and one can consider this to be the accurate choice for the generalization of GR, where the generalized field is considered by alliance between the geometric part and the scalar field with the self-interacting potential function. The problem is, or the difference is that self-interacting potential function and a scalar field and a geometric part of the field equation. What is that? This theory, because results in the acceleration of dark matter and its remodeling gives some phenomenal solutions in gravitation and cosmology. Okay, so this will give us some solutions that is very applicable in gravitation and cosmology. For example, perfect fluid cannot hold up this acceleration, whether a dissipative anisotropic can steer it. Okay, the BD theory has suggested suitable solutions to various cosmological issues, but remain unstable to demonstrate, unable to demonstrate the graceful exit of the primordial inflationary model. Okay, so this is really very good thing. One can get the simple system from the complex system in the BD theory. Dr. Rabab Manzoor did work, a lot of work in this theory, Brownswick theory, and she explained an extraordinary work on the inflationary cosmology and also the dynamical problems of stellar systems in this theory. She described that how the BD theory is affected in the description of Rai-Choudhury equations, in the description of structure formation, and the description of gravitational collapse, and many others. So we can call this BD theory to be a very suitable solutions to various cosmological issues. Okay, one can address with the help of potential function UFI in the domain of BD gravity, such as self-interacting BD gravity, that is SBD. Okay, there exists many literature related to dynamical behavior of cosmological models in self-interacting Brownswick theory, which is an example of dilaton theory, in which the dilation is self-interacting with the help of UFI. What is actually dilaton? It is a hypothetical particle of scalar field. Okay, we have a scalar field, and there is a hypothetical particle of scalar field that occurs in theory with extra dimensions. So we can call this to be a dilaton. The potential function phi, which determines the range of this field, and the basic notion of a scalar field is that it links energy with a self-interacting potential. This is really a very beautiful thing that one can see in the Brownswick theory. And I told you the chameleonic Brownswick theory, it's a special type of Brownswick theory. Okay. And next we have a quasi-homologous evolution. I told you earlier that what is the quasi-homologous evolutions? In this is the condition that we should apply on when we apply on the object. Then we have an object whose fluid forward velocity is directly proportional to the proper radius r. Okay, so this is termed as homologous condition. And then there are some authors who suppose a considerably less restricted condition to account for the evolution pattern, and this is called quasi-homologous evolution. Okay, so we know that what is self-gravitations. I told you that if there is no self-gravitation, then all the particles in it will fall apart. Okay, these are some particles. If there is no gravitations, they will be fall apart. Okay, they will move away from each other. They are driving apart. Okay, and what is next? We have alternative theories of gravity. Okay, I told you earlier, if we have Lagrangian, what is Lagrangian? Total energy of the system. Okay, when I call this to be L is equal to T minus V, kinetic energy minus potential energy. Or we can say that kinetic energy plus into minus V. So total energy of the system called to be Lagrangian. One can get the Hilbert action from the total energy. Okay, according to the Einstein, the space self-gravity system, or we can say that structure and matter interrelated. So we call matter, we can write matter effects in terms of Ricci scalar R, Ricci tensor R alpha beta, and Riemann tensor. So the introduction of R was presented by Einstein in his action, which was called to be Einstein-Hilbert action. One can easily provide the alternative theories by replacing the R with F of R. Okay, then we have F of R theory. Then we have a system which is called as equation of motion having an order, fourth order. Because of our gravity, we get the partial differential equations, or we can say the set of partial differential equations, which are of fourth order, and they are non-linear in nature. Okay, but in CBD, action function contains L phi plus f of phi Lm, where Lm is a Lagrangian density of scalar field, phi including a non-minimal coupling with structure. And what is f of phi? Is a coupling strength of fluid form distribution. F of phi is an analytic function of the scalar field. These terms, what is this? F of phi terms enables a direct connection between CDM. What is CDM? Cold dark matter, and BD cumulonic scalar field. The formation and evolution of wide scale structure is an astonishing topic in the cosmology today. Okay, I think I told you very good material. I speak very good material or enough material. It's I think you should tell me whether it is good or not, but I should tell you that it's a good heavy material on Brans-Dick theory, cumulonic Brans-Dick theory, etc. Okay, so I told you what is BD theory. Actually, it's in its action function we have L phi plus f of phi Lm into minus g square root d for x, where g is a metric is the determinant of the metric tensor. You know that actually in standard CBD model, cumulonic cold dark matter is considered as successful model in this context, which depends upon scalar invariant spectrum. The CDM is considered as a type of dark matter in which the fluid particles move slower than the speed of light. So it has a specific form, mathematical form, which is expressed as in the form of inverse of the gravitational constant and fluid configurations, and the Ricci scalar, and also strength of CBD can be determined with the help of its letter omega. Okay, it gives us two different field equations. In 1961, there was a person who was Brans and Dick. Okay, they presented this theory. Okay, they presented this theory in 1961, and that provides an alliance between the geometric part of the field equations and scalar field. Okay, and the last one is that a coupling BD constant omega BD, as I told you a few seconds before, that a coupling the BD constant parameter omega BD can be used for the correction of the observations. Okay, correct. I want to correct something, because if we have radio, I want to tune them. So I would really give the tuning with the help of some buttons, that 102, 102.1, 102.2, 102, 102.3, etc. So one can tune this. So one can also correct the observations. And next I have field equations. So these are the set of two field equations that came from the CBD field equations. Okay, in which we have G alpha beta to be the Einstein tensor, T alpha beta is the Najim tensor, and omega is the omega. What is omega? Listen. I have a problem. Yes, here it is a covariant derivative, and phi is a scalar field, and T is a trace of Najim tensor, and phi is again a scalar field. And what is box here? It is actually the D-Lambert operator, which can be expressed in terms of covariant tensor in a specific way. Okay. So what is cumulonic Brans-Dick theory, CBD theory? The non-minimal interaction of a scalar field with matter was proposed by an additional term f of phi in the Lagrangian density. Okay, and it is called to be a cumulonic scalar field. And what is f of phi? Actually, it is an analytic functions of scalar field. Okay. Das and Everanji took the initiative to determine CBD theory, and if f of phi is equal to 1, one can get the usual BD theory. Okay. Das presented this result in 2008. Okay. So these are the field equations. G mu is equal to T mu effective, Q mu effective this one, and f of phi, and I told you earlier, it is analytic function of the scalar field, and T mu matter, it's actually the mathematical expression of the matter constituents that is assumed to be coupled with the geometry, and what type of geometry will take, what type of fluid will take, I will describe after few slides. And T mu phi is here, and this is another form of equations. Okay. So what quasi-homologous evolution? This I told you V is proportional to R. Okay, that evolution of a stellar object said to be quasi-homologous if the rate at which the matter is dragged in toward the center of the object remains constant. It is a less strict condition that V is proportional to R. It remains constant. Because when we have V is proportional to R, then one is equal to V is equal to constant R, and one we have V over R is equal to constant. What motivated me to do research in these directions? First of all, Harara. He presented the complexity factor. He presented the main issue of the complexity factor in his calculations. He found that the object is complex, and it has there are many factors who are trying to make it to be complex. So we need to study what are the factors that are responsible for creating complexity in an object. So Harara done in 3 different research articles in 2018, in 2019, and 2020. Okay, because once the complexity factor on the matter position has been established, the evolution pattern of the relativistic fluids is a topic of concern. Actually, here Harara in this paper determined the models of evolution by considering them to be the simplest one. He evaluated a definition of complexity of time for time dependent, independent, because there was at that time the spherical symmetric celestial object was static. So this case requires a description for the evolution of fluid, which was strongly described by the homologous conditions, considering it as the simplest evolution pattern. Okay, and then this work was, there were work who actually who worked on Brownstic theory, and it was M. Sharif Atal, and the other author may be Sarah White. Okay, so they did work on Brownstic theory and chameleonic Brownstic theory. Okay, in 2012 and 13. I took this theory, I took the notion from this, and also I did some works which was recently published in European Physical Journal Plus by the Springer in 2022. I would like to extend their works in Brownstic theory and try to get the impact of non-minimal coupling with structure and the coupling strength of the fluid distribution, and with the help of these Brownstic theory. So what is our research work? My research work is that, first of all, I will take a line element. So let us consider an isotropic fluid. Line element of spherically symmetric relativistic fluid distribution is given over here, in which A, B, and R are the metric coefficient. They are assumed to be A square, B square, and R square assumed to be positive. Okay, and DS square it is actually the metric that can be positive, that can be negative, that can be equal to 0. Here I assume that DS square is greater than 0. Okay. Now the matter distribution, which is assumed to be coupled with equation number 1, is given over here, in which we have rho is the density, pi, mu, and lambda. It is actually the anisotropic tensor. Okay, Q is the heat flux, V alpha is the 4 vectors, and chi is alpha 4 vector. And what is H mu lambda? It is actually the projection tensor. It has specific form, in which here we have pi, P, this is P, this is pi, anisotropic tensor, isotropic fluid, and what are days are defined with the help of this one. And this is a projection tensor. Pi is PR minus PT. What is PR? It is we assume that actually I will try to tell you that I assume that our system is coupled with a fluid which is anisotropic in nature. Anisotropic means directionally dependent pressure. It has a directionally dependent pressure. So there will be two pressures, one along the radial direction, another is perpendicular to that one. The one which is along the radial direction is represented by PR, another which is perpendicular to that one is represented with P pulp. Okay. And we define P to be 2 times P pulp plus PR over 3. And this is the anisotropic tensor. Who is controlling this tensor is the pi. What is pi? Is a difference of anisotropic. Or we can say that if pi equals If pi is not equal to 0, then the fluid is anisotropic in nature. Okay, because if pi is equal to 0, then pi minus p per, what is it? That will be equal. So it means that there will be an isotropic fluid. Then we have a non-directional dependent fluid distribution. Okay. Next, for CBD theory, the field equations are found to be here, 0, 0 component. I told you that if we have a field equations, it means we have a partial differential equation. And that differential equation, not a single one. It is a set of differential equations. Many, maybe 16, and maybe 4 by 4 16, and 5 by 5 matrices 25, 6 by 6 36, etc. Okay. So 4 by 4, so 5 by 5, 5 rows and 5 columns, and then 6 by 6 means 6 rows and 6 columns. So with that, and that from them we get the some independent and some dependent differential equations. Okay. Here we have T0 effective to be equal to here, and what are B, what is B, what is R? These are actually metric coefficients, metric coefficients, and what is A? It is also metric coefficients. Where it comes from? It actually comes from this geometry that I took here, M1. Okay, so it means all of these are equation of motion or the fact of differential equations are actually representing spherically symmetric space-time coupled with anisotropic radiating matter distribution in the CBD theory. Okay. Similarly, we have the 0, 1 component, that is the non-diagonal component, and where we have this equation 1 over phi f of phi T01 m and T01 phi, which is over left hand. It is left hand side is equal to this one. Okay. And then we have another component, 1, 1 component, and then we have a 2, 2 component. Okay. 2, 2 component means that if we have a matrix like this, okay, then we have in this matrix, we have actually, yes, like this. Okay, this is actually the matrix, for example, here. Then we have different components, 1, 2, 3, 4, okay, and then we have 1, 2, 3, 4, and again 1, 2, 3, 4, and 1, 2, 3, 4. Okay, so these are some, there are some which are diagonal terms, and there are some which are non-diagonal terms. Okay, so this is actually the T22 means it is here. T0, T1, 0, 0, T11, T2, it is here. Okay, that's the component. So this actually field equation, this one, this actually comes here. And what is this? This actually come here. And what was in the previous slide, that will come here and some there. Okay, so we have different types of field equations. So these are set of field equations. Okay, so we are playing with differential equations or partial differential equations or set of partial differential equations. And next we have a wave equations. But where it comes from? It comes from the previous slide. Here it comes from, because of CBT theory, we have 2 different options. This is called wave equations. Okay, so this comes from that one. I put the value here and get this value, and then what the second equation gives? That give me the wave equation corresponding to spherical symmetry space-time coupled with radiating and isotopic matter distribution. Okay, and what is complexity factor? The factor which is trying to control the complexity of the system. The system was initially supposed to be less complex. The system was initially supposed to be less complex. So what is the factor which is trying to induce the complexity in the system? What are the amalgams of various kinds of factors that are responsible for producing complications in any structure? So we call this to be a complex system. The phenomena, because the phenomena of complexity has gained much attention on our at astrophysical scales, such as self-governing objects. The self-gravitating structures provide significant pieces of evidences regarding the origin and evolution of some obscure cosmos. A comprehensive study on these structures reveals that their intricate features depend on various physical parameters such as pressure or pressure anisotropy, heat distributions, radiation density, energy density, either it is homogeneous or inhomogeneous, luminosity, etc. These factors are accountable for generating complexity in self-gravitating complex systems. So one may need to study what is complexity here. So the effect of energy density and pressure anisotropy on the system evolution determined by YTF. Okay, so what is the factor which is responsible for the measurement or for the accountability of, okay, for the accountability of complexity is YTF. So what is YTF? This is another question. If one knows the YTF, then it knows the complexity factor. If I keep this YTF to be equal to 0, then we have less complex system. Okay, so it means what is YTF? I need to study that one. If I know the YTF, I can easily define what is the factor that is responsible for producing the complexity in the system. So this is YTF that is found in our system. What was my system? My system was spherical in structure, which was coupled with anisotropic heat rating spherical matter distribution, and then I use the CBD theory. I use the equation of motion provided by Das, etc., or Branch and Dick, and then I came to know of this YTF. Okay, this factor is responsible. What is A here? This is a function of TRR, and R is function of TRR, and phi is a scalar field, etc. If I took the specific forms of these and I get the value of this. So above equation depicts that factor of anisotropy, physical quantities such as pressure anisotropy and energy density regulatility due to YTF and the curvature terms of the CBD theory. Okay, hence YTF gives maximum information to acknowledge the complexity of the system. Therefore, YTF measures the extent of complexity in an appropriate way. Because if we know the phi, if pi is equal to 0, then the system will be equal to 0. Okay, then you know that heat flux, this is heat. If there is a system who is not producing heat, then Q will be equal to 0. Okay, and of course we have a homogeneous energy density and inhomogeneous energy density, and then we have scalar fields. So the complexity factor of YTF combining with other structure scalars along with kinematical variables reduced to this one. Now this is YTF M, and if I combine it with other structure formation, other structure variables, for example, A is for acceleration, sigma the shear tensor, theta the expansion scalar, and then we get the YTF in a specific way given over here, where YTF matter is equal to epsilon minus pi by 2. This is, and what is YTF phi? YTF phi is here. And that YTF phi is actually it is, yes, YTF, it is actually dependent on phi and other terms. Okay, so this is part is due to the general relativity, and other part is due to CPT theory. And what is YTF phi? This is here, and YTXT here. And equation 11 is used to measure the complexity factor of the systematic distribution. Our model needs to show that YTF is equal to 0. Because if we have a less complex system, then I need to put YTF is equal to 0 in my calculations. What is quasi-homologous evolutions? For this, we have the CBD field equation 4, that is the fourth one of the field equations, can be written over here with the help of some calculations. Okay, where sigma is a shear scalar and Q is a heat conducting scalar, and this is the 0,1 component of the field equations. And which on relation provide this one? 15. If the integral disappears, okay, which one? This disappears. If this appears, then we have this one. Okay, how it disappears? What is the condition that will make it to disappear? Which is this? If we take this to be equal to 0, QH can be redefined as, okay. Now kinematical constraints are radial velocity. So this is the kind of one can define dt of delta L by delta is equal to 1 by 3 theta plus 2 sigma, okay, or this one, because one can get the value of sigma, sorry, theta, which is the expansion scalar. This is not the angle, this is the big theta, that is the expansion scalar. It has a specific form. One can calculate this form from the data points, and then sigma, and after putting substituting their values, one can get this equation number 18. And then we have sigma and theta to be equal to this one. When delta dt of delta is equal to 0, we have v tilde not equal to 0, then sigma to be equal to minus v tilde by r, which is equal to minus theta by 2. One can get these calculations. One verify this calculation by viewing the previous slide. And question 14 can also be done here. What is 14 here? This one, okay? This one. With this one, and then which one in relation with respect to r gives this value, where xi of t is an integration function. V tilde is over here. One can get the V tilde from the previous question. When V tilde is equal to 0, then dt of delta is not equal to 0. Then from equation 18-19, QH condition can be written in this form. Okay, this is a condition that I found in this theory for the spherical symmetric space-time. Let's we have a dissipative case. Dissipative case means in which we have non-zero heat conduction vector. Then we have V tilde is equal to a number delta r by dt, which is equal to 0. This implies r is equal to r of r. If I put this to be equal to 0, then r is equal to r of r. Okay. Then theta will be equal to, or sigma will be equal to beta b dot over ba. What is theta actually? It is actually the expansion scalar, which if it is equal to 0, then our system is expanding. If it is less than 0, then our system is not expanding, rather it is contracting. And if it is equal to 0, then it will present a specific phenomena under which a vacuum cavity or Minkowski cavity occurs within a spherical symmetric space-time around the center point r is equal to 0. And such kind of condition could be helpful in describing the cosmological voids, okay? So under this condition, we have these two equations, which gives this one, which your integration a prime is equal to br d of t, or b dot is equal to a into small dr of d of r theta phi, where we have this equation. Okay.
Dr. Zishan, sorry for the interruption. Can you please wind up in 5 minutes?
Okay. Now the
Thank
t derivative of question number 28 and r derivative of 29, by combining above these equations, I get these values. This one, okay? But the solution here, the solution is given over here, okay? So this is one of the metric option. Now derivative with respect to t of the equation number 35 gives this one, and from equation 31 and 35 we get this one, okay? And feeding back these equations, we get d is equal to 1 over ct plus alpha. Now inserting these equations in equation number 30, we get such values, and then this one, where the shear tensor is found to be dt phi, d tau phi by b. It has a specific form. So what is it? Actually, it is a shear scalar, which is trying to create a shearing effect in a spherically symmetric space-time. Now the alternative, finally the field equations are found to be these in this form, in which we have tau and different terms that I found previously. To generalize our model, we take R A is equal to R and B, where D is equal to this one, and then the field equation turned out to be this is a 0, 0, 0, 1, and 1, 1, and two components of the field equations. So these are our solutions. What I conclude that my first conclusion is that gravitational effects of scalar field play an important role in the evolutions, because in every terms, even the YTF, even my models, there was a phi, and it is trying to present, it is trying to induce very, very important effects in our study. Now, exact solutions CBT are found, whereas analytic solutions, there were analytic solutions in GR. So dissipative and non-dissipative models are found to be more realistic in CBT theory. Dissipative and non-dissipative models, these are very interesting models that I discussed in this here. So thank you very much. I would like to say special thanks to Dr. Sai Shiftakhar Saiba and other thanks, and also special thanks to Dr. Rubam Manzoor and Dr. Taiba. Yes, this is all from my side.
Thank you so much, Dr. Zishan, for such a nice presentation and for your precious time. So, any questions from the audience? So I think there is no question. So, Shabnam Ashraf. Okay, I think a very quick one question. Ms. Teba, if you can unmute Shabnam or Sadia.
Great. Okay.
Sadia, you can unmute yourself. Yes.
Assalamualaikum.
Hi.
Sir, I have a question. That if we change the theory of gravity, like FFR gravity or any other, then how it will affect?
How it will affect on which one? What you want? Or affects on which? Okay, maybe your question is that what are the effects of modified theory on the dynamics of theories, systems? Am I right?
Yes.
Is it your question? Yes, very good question. Thank you very much for raising such a nice question. The problem is actually is that when I try to induce an alternative theory of gravity in our equations, then it means I'm trying to induce the extra amalgams of curvature ingredients. Who is trying to calculate the curvature ingredients are the Ricci scalar, Riemann tensor, Ricci tensor. Even according to Einstein theory, the geometry field, geometry and matter are related with each other. So that's why one can induce. Some people say that one can induce the trace of energy tensor also in it. So it means we are trying to get more and more effects of curvature through Ricci scalar, Ricci tensor, Riemann tensor, even the contraction of the Ricci tensor with its Ricci tensor.
Excuse me, Dr.
Actually,
Zishan, sorry for the interruption, but you have to rejoin on the same link.
okay, thank you.
I am Mohammed Azhar Ehsan, Associate Research Scientist at IRI, and I am ENSO and Climate Forecast Lead at IRI. I was listening the last talk, so it seems my talk is way much simpler than the previous one. We don't see many equations, while we see many graphs and visualizations, as we climate scientists usually do. So before going into introduction of El Nino Southern Oscillation, I would like to introduce myself. So I'm a climate scientist, and my journey starts from Global Change Impact Studies Center in 2007, when I joined NCP, National Center for Physics, as scientific officer. Then I moved to Saudi Arabia. And during that time, I was the junior associate at ICTP, International Center for Theoretical Physics, Italy. Then after my PhD, I joined ICTP as a long-term visiting scientist or postdoc. And from ICTP, I moved to IRI, Columbia University, as postdoc for initial 2 years, and then promoted to associate research scientist in September 2021. I worked in different projects, as in typical US in US universities. My track is research. We work on different projects. My current projects are in Ethiopia, Bangladesh, US, Canada, Madagascar, East, West Africa, and we have several in few in progress with Saudi Arabia, Egypt, and we submit in Pakistan as well. So let's see. After, I like to introduce my institution. So IRI basically works in climate and its impacts. We have collaboration with governments and development organizations. We work in, at IRI, we work in the forecasting, in ENSO, in climate, and typically we worked on the near-term climate forecast, like seasonal, subseasonal, and decadal timescale. Less on the climate projections that we usually hear on the news. So we have different our partners in research, relief, donors. So like our research organization, our National Science Foundation, NOAA USA, and donors are USAID, US TOS, that typically works in different countries. In Pakistan, they definitely have this different calls for the projects. And then donor agencies like World Food Program, International Red Cross, and World Bank, all these. So I like to show that two of the projects that I worked in. One was the Act Today Colombia. Act Today was adapting agriculture to climate today for tomorrow. So it's a complete project. It was in 7 countries. This name are written there: Bangladesh, Colombia, Ethiopia. I worked in Bangladesh and Ethiopia. The other countries were in Latin America and one in Africa. So it's a first Colombia World project where they worked in those 7 countries. Unfortunately, COVID arrived, and then most of our work was off online, not on ground. But lately, in the last year, there was a lot more activities happen. So, and then this project led to another one. While it was ending, there was another World Bank project called ICRA, which is accelerating impacts of CGIAR, climate research for Africa. So, which is $60 million project in Africa. IRA is leading in the climate side of this project. Again, it's in these countries: Senegal, Mali, Ghana, Ethiopia, Kenya, and Zambia. So, and then one thing I like to show about my institution is our flagship product, which is ANSO forecast that IRA is issuing since 2002. So this is nearly a 2-decade of research and service that IRA is providing. So we'll talk more about about this product during this talk. So enough about introduction, myself and my institution. Let's talk about the outline of the presentation. So as I said, this talk is more on visualization and more simpler than these webinar talks, which are more mathematical. But it has a great societal impact. So my first slide is about setting the stage. So first one, most of this material comes from Wikipedia, which is acknowledged at the end. So 2002 Pakistan flood. So around 1,800 people killed. And look at the number of loss in number, economic loss, $15 billion US economic losses. So 1,800 people killed, and then about $15 billion loss. That's a aerial picture in August last year, 21, and this one is August 27, 2002. We can see the extent of the flooding. Then it is highlighted in several places, like UNICEF, some peanut grants of 4 million from different organizations, like I think Japan government gave something. Personal loss of life and property and loved ones. During this time, from July, August, September, I searched just NY time because I know there was a lot of media requests. So about 15 plus articles, just New York Times, talking about floods in Pakistan. And then this, we know this is a famous tweet by Antonio, UN Secretary General, about talking about Pakistani monsoon and its damage that happened during that time due to this monsoon. Is this a common thing? Or sorry, rare thing? No, it's a pretty common. In 2010, we faced the same thing. And if you compare the numbers, it's pretty similar. While the number is increased. So 6 million, now I think it says 33 million or something like that. So, but we are facing in 10 years ago, same thing in 2010 flooding in Pakistan. And if I go a little bit back when we have this record, and in 1992, there was another flooding. So again, 2000 plus deaths and a lot of course, economic loss. But that's the flood is not the only problem. The other problem is drought, which usually go unnoticed. I mean, we don't remember or don't realize that there's another problem, which is even more severe than the floods. Floods come, destroy, go away. But drought is another problem. So usually in our southern Pakistan, like in district Tharparkar, in areas of southern Punjab, in Sindh areas, in Balochistan areas where this thing happens, drought conditions. It's the other side of this impact. So now I just thought to compare this one with our numbers. So our exports in 2019 about $30 billion US dollars, and if our current exchange is even bad from this number, so it's currently showing 9,000 nearly 9,000 million, but yesterday news was about 7,000 million US dollars, and you look at the loss, it's 15 billion, almost double. So so our current foreign exchange and our loss in like 4 months ago is like almost double. We need to think about this one. So points, flooding during monsoon time typically is cause severe damage to Pakistan, loss of life, damage to personal property, governmental infrastructures. It's like a very tempting thing to assign this to climate change, that climate change is cause of this one. Yeah, climate change is playing a role, but there are several other things that we need to keep in mind or should consider. So to save life, conserve resources, save our resources, we should better understand what's going on and become a climate ready nation. So I have one example. During this week, one conference was going on. It's just concluded yesterday by WMO, World Meteorological Organization, scooping workshop. Who is organizer? It's a WMO. It's a UNO entity in Weather and Climate Services. So where it is happening in Pune, India, in co-organized by IITM and IMT Pune. So people are caring about El Nino and La Nina information and their impacts on their society. So there are about 50 participants, and I looked at the list and none was from Pakistan, mostly from India, Japan, Europe, US, everywhere, but not. So it seems we need to do a better job in terms of understanding and our knowledge about this phenomenon. So from IRI side, my supervisor, Andrew Robertson, was there, and we presented our IRI and information products. So enough about the setting the stage. Now let's start some simple statistics or mathematics. But before that, we need to a little bit, I like to give know-how about the climate data set. So here we use sea surface temperatures. So climate data, now this is a screenshot from IRI data library. It's a data hub of the climate data sets. Millions of, I think a huge number of data sets are available. I can say from all over the world where we have the projects. But there are some common data sets that are also available there. So one of them, for example, we are using here is sea surface temperatures. So how climate data arranged is in the time, it's in the grids, time grid, longitude, latitude, and levels as well. So for example, this data set I selected is starting in January 1854 and running towards the recent last month, which is November 2022. So it's a monthly data set, months, so about 2000 plus points. And these are also arranged in X, which is the grid running from east to west, 180 points, and it's a by 2 degrees, so it's a 2-degree resolution. And then the latitude wise, which is in north and south direction, is 89 points. So it's another screenshot if we like to view this data set, and we can see the information on this graphics. So X, Y, Z level, and time selection, and then the view in different colors. And if we click in one of color with ghost, we can see that the most recent figure graph appears, which is November 2022. So point I like to mention, make here is how the climate data looks like. It's in the time, latitude, longitude grids. So that's the data set we used here. So El Nino Southern Oscillation, I define in the last, not in the initial. So first we look at what in visualization, that how and what the ENSO is. So first, very simple equation I'm showing here. So no need to explain how we calculate the mean. So, but the figure is interesting to look at. So this is December, January, February sea surface temperatures mean over 1991 to 2020, last 30 years. In climate science, we also called it climatology, and it's in degrees Celsius. This is the scale. Different colors shows different numbers. It's by 2 degrees. So 0 degree, I started from 0, then 2. Next color is ranging, showing the value 4, 6, and 8, and so on. It go up to 32. And you see some pattern here. So from poles going to this black line is equator, and this line is 0 degree latitude. It's a date line. Not date line, sorry, 0 degree latitude. So this is a pattern there. And we see something, we try to play something interesting here. Indo-Pacific warm pool, this area, dark color. What is this one? I try to highlight this area. This area is very important. It's a pretty big area, about nearly not half, then more than 1/4. And some typical characteristics of this area include is that temperature is greater than 28 degrees centigrade during the time of the year. So that's why we called it the heat engine of the globe. The second most important thing is that, so when it's such a high sea surface temperatures, then it could creates convection. So when convection happens, then it becomes the steam engine of the world. So this area. So what does it mean? We look on the right side, this is a precipitation. So look at this area. It's the month is July, and you can see that other than any other parts of the world, this area is producing a lot more precipitation. Huge precipitation over this area. This is Indo-Pacific warm pool region, this area. So from the mean, we see that there are some pattern here. It's interesting, but not much interesting. Let's go to the next order, second order statistics, standard deviation. So when we do the standard deviation with the same December, January, February SST data set, you know, this standard deviation formula, we get this one. So this is standard deviation. And now immediately we see, as compared to this one, we see a pattern here in the Pacific. Now, I'm sorry, I suppose maybe I need to. So this is also, we need to know the ocean. So this is Atlantic Ocean. This is Indian Ocean. And this whole Pacific is from South America to Australia. This is Pacific. So we see this pattern. Very strong variability. If you read the scale, then this color, darker color, is about nearly 1.2 to 1.4. Again, this is at I think 0.25. So so this one darker color is 1.5 degrees standard deviation. So meaning that during the time of a year, this area can have the the values which can go beyond the mean values. How it looks like. So let's remove these square roots and things like that and look at the simple thing, which is deviation from the mean anomaly. So now I'm defining the types of ENSO. So number one, two graphs appear here. So one is December, January, February 2015 and 16. Another is December, January, February 2021, 2022, last year. We can see two interesting patterns. Warm. Now scale minus 3.5 to 3.5. Difference from average. We can see the values are nearly near the equator, close to 3 degree positive anomalies. Warmer than normal. This is called El Nino. And you can see there the bluish color. So this is called La Nina. So this means that it's below average, colder temperatures across in the Pacific. So El Nino Southern Oscillation typically gives us two main flavors. One is warm and other is cold. So these are called ENSO types. But in between these two, we already saw this one, so I go quickly from these two slides. So we have La Nina, where we have the cold temperature in the Pacific, El Nino, where we have the warm temperature in the Pacific, and then the neutral is this one. So there are several other things which I don't like to go because there's might not be much in need another full series of lectures to explain the ENSO complete dynamics. But here you can see that in neutral phase we have this circle, with a thin line. Cloudiness over maritime continent region like Indonesia and these parts of Australia. So when the La Nina happens, we see this cold extend, these things get strengthened. So this circle, atmospheric circle, get strengthened. We have high, more intense cloudiness in this region, and Australia received a huge amount of rainfall over its over their eastern side, eastern half of Australia and maritime continent region. So while this one, El Nino, is the other flip side. So now this big circle is break up into two. So where we have now the convection center shifts from maritime continent to central Pacific. So in short, we have two main flavors: La Nina, cold; El Nino, positive; and neutral is the state. So then we maintain a history of these El Nino, La Nina events because of their impacts around the world. So I just take a screenshot from 1991 to 2022, most recent one. And also there are different El Nino regions. So like 3.4, 3.4 regions, we called it Eastern, Western, and Central Pacific, and Far Eastern Pacific near Ecuador and Peru as well. So these are used to define different El Nino regions, but typically we use 3.4 Nino region. So, and at this point, I like to define ENSO. So ENSO is a couple phenomenon. And couple mean it's an ocean atmospheric phenomenon. So what happened when there is some change in ocean atmosphere response, or if there is changes in atmosphere, then ocean response, give a response. So it's a couple phenomenon in ocean atmosphere. So this is a typical definition of the ENSO. Why we care about ENSO? Because its impacts across the world. So La Nina and rainfall, El Nino and rainfall. So that's a work that was done like 20 years ago, and then the recent update in last year of this one with how El Nino and rainfall and El Nino and rainfall happen. So we can see color coding. Dry is yellow and wet is green. So, and then the month is mentioned. So like, for example, if there is La Nina, we expect the Australia maritime continent regions during May and February, September, March, they are getting rainfall, which is more than their normal rainfall. If there is El Nino, there is the typically could be reverse side. And then our region, so South Asia. So look at La Nina. So from June to October, we can have wet anomalies, and from January to May is our winter. We expect dry conditions. In El Nino, from January to April, this could be wet, and from June to September, most probably the dry conditions are expected. So this is across the world. Let's look at one just in Pakistan. So because our concern is Pakistan. So this figure is July, August, September rainfall. So given La Nina conditions, so it's a probability, not a rainfall. So probability that the July, August, September, which is our monsoon time, the rainfall could be above average. So what's the probability? So this is a scale, and we can see there are some pink dots as well, which shows the probability of 80 to 90% that rainfall.
Excuse me, Dr. Hassan.
Yes.
Can you rejoin on the same link? Sorry for the trouble.
Sorry?
Can you rejoin on the same link?
Same link? Okay. Oh, it seems like the meeting time was over.
Yeah. So you can share your screen now.
Okay.
Thanks for the patience. You can continue.
Where we kicked off? The last slide?
Yes.
Okay. So we're discussing about the ENSO impacts across the world. So during La Nina and El Nino. So, but let's focus over Pakistan. So these are the across the world, and this one is just zoomed over Pakistan, but of course we have like over India and Afghanistan, other regions as well. So this is June, July, August, September rainfall, which is our monsoon time, given La Nina conditions. So it's a probability, not the rainfall. Probability that the rainfall could be above average if there is La Nina. So you may see that there is a lot of like these red colors in particular in these in Punjab and in northern Balochistan and southern northern Sindh areas. So which means that if there is a given La Nina, there's a high probability that the rainfall over this region will be more than average. Okay, so red color is 70 to 80%, and there are some dark pink dots as well over this area. So quite high probability if there is La Nina to get above average rainfall. Okay, so that's the point we see that if there is a La Nina, what we can expect in Pakistan or in South Asia as in a regional scale. So then ENSO forecasting. So current level of skill. This is a paper that we published this year for the ORIC CGCM. During my stay in Saudi, I worked on the ENSO forecasting and seasonal forecasting, and we also developed this coupled model for Saudi Arabia, and we compare the this ENSO forecast skill of the Saudi KU model with other models. So this one is on top left is Saudi KU, and the rest is from the European, US, and Canadian models. One of the famous is Geophysical Fluid Dynamics, GFDL, Princeton model SPEAR. So this is not having a very good skill. So this is a normally correlation, and again in colors. So 0.3 is mean the lowest correlation I put here, and close to 0.9 and 1 is the highest value. So ECMWF, European model, so European Center in UK. Meteo France is an example, and then this Canadian model, they have pretty high correlation values. There are some more things in this graph is the target month on the x-axis. So you see JFMA is a target month where we start like January, February, and then the lead. So after starting in January, how long we go further in the forecast. So this is up to, you're starting from 0, so it's typically 6 months lead time. So up to 6 months lead time, this is the current level of the forecast from these models. So some of the models that show high skill in the first 3 leads, like ECMWF, Meteo France, CanSIP model, And there are few models that that have lower scale, like GFTL sphere model. So even during the summertime, like May, June, July, even after one lead forecast starts in May or in June, it quickly lose its skill. So the skill become really weak. So skill mean correlation, in this case, anomaly correlation. So that's the current level of the forecast. If you like to read more, know more, you can go and to this link and read this paper. Or there are tons of paper on ENSO forecasting. So after that, ENSO forecasting at IRI. So at IRI, we have the ENSO forecast builder that we to early month, mid-month, and plume month. So I'm just showing the anomalies here. And the next graph, which is showing the most recent model predictions of ENSO from November 2022. So now we are in December and we are preparing for the next level of predictions. So it is updated every month. It's it's called ENSO Plume, typically, and Plume, and it has like nearly 20 plus models. The model names are mentioned here. We have dynamical models from different centers, and their dynamical average with this dark, thick red line. Then we have statistical models that do the predictions. So like 6 or 7 statistical models as well. So, and their averages. And then we also published probabilities and strength of the ENSO along with that one. So that's the ENSO IRI forecasting that we are doing since 2002. It started about 20 years ago. And this is also my last slide. And my Dr. Arush knows that we are trying to build a collaboration between IRI and Lahore College for Women University Mathematics Department. So it's an open invitation to, if you would like to participate in this process, that would be really great. So to produce next generation of climate scientists that could help and inform policy holders and stakeholders about for a climate ready nation. So that's the last slide of mine. I don't have any conclusions, just acknowledgements and thanks to organizers. It was really great webinar, and thank you so much for inviting me.
Okay, now
I will
time
stay
to
here.
okay. Now time to take questions. A very quick questions. Anyone? Okay.
Assalamualaikum, sir.
Walaikum assalam.
Sir, I want to ask from you, what specific issues with ENSO in the models need to be improved?
So like this one. So one of the very specific issue, which I don't talk here, is that ENSO has a phase locking. So meaning that if we start a forecast, where is my mouse? Is it okay? So you see these months, January, February, March, April, May, June. So one of the problem you can see is a structure here. So when a forecast starts typically in the summertime and also in springtime, then we lose our skills so quickly. So this is one of, a very big issue. So for example, currently we are in now December. So one of the very important forecasting, as I mentioned in my first slide, setting the stage, that monsoon time. So if we do a forecast in February, we are like forecasting in about 3 months after. So, but the skill of the forecast is very poor. You see the green colors? Green color mean very low value, low correlation values. So model skill is low. So that's one of the, I can say, it's a long-standing problem. I mean, it's not a recent trend. It's a known thing, and but very important that policymakers and forecasting institutions and particular agriculture ministries and extensions, they like to know how the monsoon will be. So in order to know about the monsoon time, they need to know about the ENSO. But ENSO has a problem if we do in the late winter, early springtime, because it loses the scale. I'm just highlighting this model and don't to, I mean, blame this one, but overall that's a structure. So that's one thing. The other thing is long lead. So that's also related to this one. So people like to know the forecast of ENSO in a year time. So like this one, I'm showing just 6 months lead. So when we start the forecast, for example, in January, we forecast up to 1, 2, 3, 4, 5, 6 months. Like this. So long lead is another important issue that that is we and so forecasting required. Okay, I hope that answers your question.
Okay, any other
Thank
question?
you so much, sir. Thank you so much, sir. Sir, another question is, if we want to do ENSO modeling through mathematical techniques, which data is more predictable, PDO, SST, or ONI?
PDO is another phenomenon. So with the statistical models, if we like to go for a more skillful, or I can say more reliable predictions, I don't have that one in fact here, but I like to mention in this slide, is subsurface information. So we, in this presentation, I just talk about sea surface temperature, what's going on the surface. So one of the great predictor of ENSO is actually what's going on in that, because I mean, in the predictability field, in the field of predictions, we actually talk about the memory. So ocean subsurface actually keep the memory, while the surface is changing so rapidly. I mean, I don't want to add more complexity here, but the main thing is that we need to know what's going on in the subsurface, like in the Western Pacific, over this region where I'm highlighting, where we throw these stars in this area. So knowing about the subsurface temperature, which is, you can see in this slide as well. Okay, this one, you see this is the subsurface information. So knowing about the subsurface information can provide us more skillful forecast of ENSO as compared to surface and atmospheric variables.
Okay. Thank you, Dr. Azal. It's such an informative talk about climate and mathematical description. We are really grateful to you for your valuable time and sharing.
Thank you so much. Thank you.
Now, I thank all of you for participating in this tremendous research platform. It's an honor to host the webinar. for me and Dr. Sarish, obviously, my special thanks to all keynote speakers for enlightening us with their wisdom and outstanding research ideas. Thanks once again for attending the webinar on recent trends in applied mathematics and physics. Definitely, we have some value time together, and we hope that you learned valuable insight, which enable you to set up your critical thinking skills.
So I hope to see you all again. Allah Hafiz. Goodbye. Take care.
Thank you.